All right, ladies and gentlemen, we're going to look at this question. Go ahead and hit pause on the video and try it out on your own, but I'm going to go ahead and get started. So the first thing we notice is counterclockwise is positive in this question. So we're going to say that initially this thing has a positive velocity. With that, we can immediately go ahead and knock out two of our answers because those start with negative initial velocities. Which of the following could show the time of angular velocity of the disk as a function of time? Well, what is this disk going to do? So we have 20 newtons on the left, 40 newtons on the right. They both have their same radiuses or radii from the center. So that means we're just looking at torque net here. So with that being said, it's going to want to accelerate going clockwise. So that clockwise, so your acceleration here is going to be negative. So which one of these it has a negative slope the entire time? And that would be C right here. This one we would say if my object was slowing down, stopping, and then speeding up again in the positive direction. So that's not going to get us there. I do have a better question though. This one I stole from the College Board website, so be as it may. What we're going to do is really unpack this question of looking at when torque net equals 0. Alrighty. So we're going to hit pause on the video, try this question out, maybe give a sentence or answer, be able to answer each of these questions. This really isn't an FRQ, but it's kind of getting there. So using the concept of torque, explain why student B, the second student, needs to apply additional tension to put the meter stick in equilibrium. Well, what we need to say then is that the torque counterclockwise needs to equal the torque clockwise. In order for anything to be in equilibrium, torque counterclockwise has to equal torque clockwise. If we call, let's say for example, this T1 our frame of reference, we would then have to say that the torque provided by the weight, mg, because that's going to want to go one direction, is going to be equal to the torque provided by tension 2. Okay, there's a bunch of different reference frames you could use here. You could use the middle of the meter stick. You could use a bunch of different ones. I'm just going to use one. So explain why a second student would need to apply additional tension to put the meter stick in equilibrium. Well, the reason being is that we want the torques to be equal but opposite to each other. So what is the value of T2 in terms of mg? So again, sticking with saying that this is my frame of reference here, what we're going to do then is say that the torque weight equals torque T2, and so that's going to be Fr sine theta. Now the force for weight is going to be, put weight here, and that radius from the weight, and T2 is going to be, tension 2, so force from tension 2, radius from tension 2, sine theta. This is just going from the formulas they give you in your reference sheet, but we see both of these angles here are at 90 degrees, and so sine of 90 is 1, so those are just going to go away. So now we got weight, which is going to be mg. The radius from this center point right here to here is going to be the entire length of the bar, so we'll call that L divided by 2 because it's the halfway point. For T2, we're going to say the tension of 2 is the force. The radius is going to be L, and then sine theta already disappeared. So what we get here is T2 then equals, L's cancel out, mg divided by 2, or half the weight. Now, that might make sense now because this object is all in statics. But let's describe, if we start to change things, we can't really then just specifically talk about force. What we have to also talk about is how the torques are going to change. So describe any changes to the required T2 as student B gradually moves towards the center. So if T2 was here and now was here, how would T2 change? And going back to up here, So I'm going to rewrite this. So the tension from weight equals the tension of T2. Now the torque from weight, the torque from weight doesn't change. That's still going to be a static value. So we're going to put F weight, radius from the center of mass, so you can say weight or center of mass, equals T2, and then radius 2. Now, if we decrease the radius from T2 from T1, then we're going to have to increase the tension on the string or however they're pulling up on. And so as radius decreases, tension increases because the torque provided from weight will not change. All right, what happens at T1 as student B approaches the center of the meter stick? Well, if we look at it this way, we can then say, what happens if T2 is right over the meter stick? What happens there? Well, that means that all of the weight from tension 2, all the weight is being pulled up by tension 2, and so then we can then say, as T2 approaches center of mass, we can then say T1 approaches 0. All right, and that'll be it for this, folks. Good luck. If you have any questions, let me know, but this is a wonderful question looking at statics of torques. All right, guys. See you later.